Hi everyone, this is New. Well, welcome to Chapter 6 on mechanical properties. We have a lab that we're going to be doing hopefully after we resume our in-person instruction. But for now, let's learn about the mechanical properties. These are the learning objectives and the issues that we're going to be addressing in this chapter. So feel free to pause and take a look at it. Here's learning objective 1. You may want to just pause the video and take a look at it, or come back to it when you're reviewing this topic. The concepts of stress and strain will be useful when the load is pretty much static, or else maybe changing really slowly, and it's uniformly applied. So for example, the sudden load that a seatbelt will suffer if you were to get into an accident would not be something we could analyze under these conditions. But if you were to just attach it to the ceiling and then hang weights from it, slowly increasing the weights, watching it stretch and then eventually break, that's the kind of mechanical behavior that we can analyze with a stress-strain test. We define the tensile stress, sigma, as the force per unit area, pretty much as you can see in the diagram there. You basically apply equal and opposite forces, stretching the object out, and A0 is the original area before loading. What do you think the units of tensile stress are? Go ahead and pause the video if you need a little bit of help. The units are newtons per meter squared, which are pascals. In the English system, that's sometimes recorded as pounds per square inch. That is, they're the same units as pressure, a force divided by an area. How do you think you would define compressive stress based on our definition of tensile stress? Again, pause the video if you need to consider this. Compressive stress is basically defined the same way, except the stress will be negative. Here's an example of tensile stress in the real world, a cable in a ski lift. The tensile force there would just be the tension in the cable, and again, A0 would be the cross-sectional area when unloaded. People would certainly want to know about how the cable is going to behave under these conditions. Will it stretch? When will it break? And so on and so forth. Here's a real-world example of compressive stress. Here's a rock sitting on a rock column, or part of a bridge that is basically feeling forces pressing inward on it from both ends. In our definition of engineering stress, why do you think we are dividing by the area? Why don't we just call the engineering stress the load that's being applied? Well, basically, you could imagine that if the cross-sectional area were to be doubled, it would require twice the load in order to produce the same effects, that is, the same elongation or the same compression. So you need to normalize the load by the cross-sectional area that the load is being applied over, basically normalizing the load. That's what we call engineering stress. In everyday language, we often say that we're feeling stressed. However, in engineering, you should be saying that you're feeling strained because it's stress that produces the strain. We define engineering strain as epsilon, the change in length divided by the original length. What do you think the units of engineering strain are? Well, as you can see by the definition, delta L over L0, you're not going to have units. It's going to be dimensionless. Go ahead and convert the load and change in length data to engineering stress and strain, and plot a stress-strain curve. I'm going to provide the answers now, so pause if you want to work on it yourself. These answers just come from the definition of stress as being the load divided by the original area, and the strain as being the change in length divided by the original length. Here's a stress-strain curve for an aluminum alloy that comes from another textbook. Notice that there's a break in the x-axis, so it's really not to scale. Honestly, this is just a teaching diagram to highlight the important aspects of a stress-strain diagram. You're going to want to know each one of these terms, and we'll be discussing them one by one. So in real life, how do you measure tensile stress and strain? Well, it's pretty much as you would expect. You apply a stress to the material and watch the material stretch, and you basically measure the strain. You pull the metal to failure. Some of you have taken the statics course and have seen strain gauges and used them with that Pasco model of a bridge. But basically, a typical tensile stress machine just exerts a tensile force on a specimen, and a load cell measures the amount of force that's being applied, we know the cross-sectional area in advance, and we go ahead and measure the strain, and then plot a curve. Here's a stress-strain curve being measured in real time. If you look very carefully, you can see the sample begin to neck a little bit, get a little bit thinner as it's being stretched, and then ultimately it's going to break. Here we go. Almost there. It's getting thinner. And then finally it's going to... Come on, let's go. Camera shaking a little bit. Pow. Here's some data from a stress-strain curve that we can measure with the Pasco stress-strain apparatus. This one happens to be aluminum, and we'll be doing similar samples in lab. Each group might choose to do different samples like brass or aluminum or various polymers as well. Look forward to doing this after we come back. Your textbook has example problems, such as this one for a brass specimen. When we apply stress to a material, we can either have deformation that is elastic or deformation that is plastic or permanent. Another learning objective is to state Hooke's law and denote the conditions under which it's valid. You first encountered Hooke's law in Physics 153 when you were talking about the force being applied to a spring. As you doubled the force applied, the amount that the spring stretched would also double. In the same way, Hooke's law for materials says that there's a constant called the modulus of elasticity, sometimes known as Young's modulus. And it says that the stress and the strain are linearly related in the elastic region. The elastic region basically means that you have not permanently deformed the material. Just like, when you stretch a spring too far and you release it, it doesn't come back to its original shape. You've gone too far. The spring wouldn't be performing elastically once you basically push it like that. Here, on a stress-strain curve, the modulus of elasticity E is the slope, the proportionality constant between the stress and the strain. These are other names for the same thing, and in some textbooks you'll see the symbol Y used for Young's modulus instead of the E for modulus of elasticity. On a stress-strain curve, we can see that the modulus of elasticity is the slope of the stress-strain curve in the linear region, and the elastic limit is basically where that linear behavior stops. If we take a microscopic view of elastic deformation, the bonds are stretching ever so slightly, but when the force is released, the material unloads and returns back to its initial shape. So elastic basically means reversible. Let's go and look back at a graph that we first saw in Chapter 2, the force versus interatomic separation for different atoms. The elastic modulus, or Young's modulus, measures the stiffness of the material. It's basically proportional to the slope at the equilibrium bond length. Remember, the point where the force crosses the axis is the point of interest, because that is when the net force equals 0. So this measures the equilibrium bond length. dF/dr for the red material is very, very steep. For a small change in separation, we're getting a large change in the force. Whereas for the blue material, it's a little bit smaller. So that tells you that the stiffness is proportional to the slope of the force versus separation curve measured at the equilibrium bond length. We've just talked about how tensile stresses can cause elastic behavior. Well, compressive stresses, as you might imagine, can do the same thing, but also shear and torsional stresses. So far we've talked about tensile forces, shown in green, that tend to elongate or compress the sample. However, in general, a force can be resolved into both a tensile component and a shear component, shown in red. The shear stress is defined as the shear force divided by the original area. So what are the units of shear stress? Again, pause the video if you need to. The units of shear stress are pascals, that is newtons per square meter, exactly the same as those of tensile stress. When you apply a shear stress to a sample, it's going to deform as shown. The linear amount of deformation, delta x, is not a good measure of the shear strain. However, if you normalize that by the height of the sample, then gamma, the tangent of theta, is a good measure of the shear strain, and that's the measurement that we adopt. What are the units of shear strain? It's dimensionless because it's basically a length over a length. Experimentally, we find that the shear stress tau is proportional to the shear strain gamma. The constant of proportionality is known as the shear modulus. Not surprisingly, when you apply larger shear forces, thereby applying a large shear stress, you observe a larger shear strain. Here are some measured values of the elastic modulus E and some measured values of the shear modulus G. The units of each of them are basically gigapascals or pascals or psi. Not surprisingly, because in each case the stress is measured in pascals and the strain is dimensionless. Remember that Young's modulus measures the stiffness of a sample. Not surprisingly, a large E generally corresponds to a large G. And in general, the Young's modulus for ceramics is greater than that of metals. That is, ceramics are stiffer than metals. And both of these materials are much stiffer than polymers. Remember that elastic modulus refers to the slope of the linear portion of the stress-strain curve. However, if that portion of the curve is not linear, we have to come up with some new definitions for stiffness. This figure shows how you can define the secant modulus as the slope of the secant line between the origin and a particular value of stress, sigma 1. You can also define the tangent modulus as the slope of the line that's tangent to the curve at a particular stress value, sigma 2. Notice this particular concave down portion of the stress-strain curve. It shows that the material is less stiff at larger values of the stress. Let's do an example from the real world. This is an art installation at the Seattle Art Museum. Suppose that you're suspending a bunch of cars from the ceiling using an aluminum rod with a circular cross-section. It's got to withstand an applied tension force of 200,000 newtons. We don't want the rod to break, so the maximum allowable stress is going to be 175 megapascals. The artist wants a rod that's at least 4 meters long, and we don't want the rod to deform elastically more than 0.65 centimeters when the 200,000 newtons is applied. Of course, if we use a very, very thick rod, all these conditions can be met. But the point is to try to save some money and be efficient and calculate the minimum radius of an appropriate rod. You should pause now and work the problem because I'm going to go over it right now. All right, here are the hints. If these are enough, again, you might want to pause and work it out. Otherwise, we'll talk about it right now. So the strain is 0.65 times 10 to the minus 2 meters divided by 4 meters. We plug that into Hooke's law. We look up the Young's modulus for aluminum, which is 69 gigapascals. So multiplying 69 gigapascals by the strain, we find a corresponding stress of 112 megapascals. We want to compare that to 175 megapascals. Obviously, it's less. We go with a smaller value here, 112 megapascals. In other words, the stress had better not exceed 112 megapascals, because otherwise the strain is going to be more than 0.65 centimeters. Now that we know that the stress is 112 megapascals and that the load is 200,000 newtons, we can go ahead and calculate the original cross-sectional area of the rod, and that gives us R equals 2.38 centimeters. Suppose we had a very conservative engineer and the stress is not allowed to be more than 99 megapascals. In that case, we set 99 megapascals equal to 200,000 newtons divided by pi r squared, and we find that a thicker rod must be used, 2.54 centimeters. On the other hand, suppose we had a really loosey-goosey engineer who's going to allow the 4-meter rod to stretch as much as 2 centimeters elastically when the load is applied. In that case, the strain is 0.005. That's just 2 centimeters divided by 4 meters. And we find that there's a corresponding stress of 345 megapascals there. However, we still don't want the stress to be more than 175 megapascals, so that's the value that we go with, and we find that the radius can be 1.91 centimeters. In other words, when the stress is 175 megapascals, the rod will stretch 2 centimeters if it's 4 meters long. So that's why we're allowed to use something a little bit thinner than 2.38 or 2.54 centimeters. A few slides back, you may have noticed the column labeled Poisson's ratio in the data table. Here's a learning objective with respect to Poisson's ratio. Take a look at the picture and maybe stretch a rubber band back and forth in your hand as you look at this slide. The concept is that if you apply some kind of tensile force and you stretch the material in the z direction, that the material will also change shape in the lateral directions in x and y. And so therefore we define Poisson's ratio as the ratio between the lateral and longitudinal strains in the elastic region. That is, when you let go, the material springs back to the way it was originally. Okay, so Poisson's ratio is defined as minus epsilon sub x divided by epsilon sub z, or minus epsilon sub y over epsilon sub z. Notice that we're assuming some kind of axial symmetry in this case. Why do we expect the minus sign to be there? Well, basically, again, looking at the diagram, you see that there's going to be a stretch in the z direction, but for most normal materials, you expect that the y and the x directions are going to be getting a little bit thinner. And so those strains are going to have opposite signs, and we want Poisson's ratio to come out to be a positive number. Auxetics are materials with a negative Poisson's ratio. That seems really strange, but basically when you stretch it in the z direction, it can also stretch in the x and the y directions as well. So it's really just mentioned as a point of curiosity. We're really not going to do any problems in this class about it, but it can happen. Here's a problem that I would like you to solve. And again, pause the video because I'm going to go over it immediately. So what you do is you take a look at the load of 48,800 newtons and you calculate the stress by dividing by the cross-sectional area. You're going to find that the stress is 1.72 times 10 to the 8th pascals. You then set that equal to Young's modulus multiplied by the strain. That helps you find the strain of 2.49 times 10 to the minus 3. You can change that to a 0.50 millimeter elongation of the material. Okay, so now that we have that, we use the Poisson's ratio equation and we can find the strain in the x direction. That's going to be minus 8.217 times 10 to the minus 4, which means that the change in diameter is going to be minus 1.56 times 10 to the minus 5 meters, or minus 0.0156 millimeters. The sign is negative because we're elongating in the z direction and we expect the sample to get thinner in the x and the y directions. As you might expect, there is a relationship between the elastic modulus, the shear modulus, and Poisson's ratio. Here's the relationship for isotropic materials. So far we've been talking about elastic deformation, one where the material returns to its original shape when the load is released. Now we're going to start talking about plastic deformation. That's when the material permanently deforms. This slide pretty much says it all. You apply a very, very large tensile force, you get some deformation, part of it is elastic, part of it is plastic. When you release it, the elastic deformation is recovered, but there's still some plastic deformation left over. That is, the sample has permanently changed and will not return to its original shape. Here's a diagram from another book showing what happens when you apply a large force to a single crystal of metal. Afterward, there are step markings on the surface, which we call slip bands. This material is not going to return to its original shape, even after the load is removed. Here's a thought question for you. In engineering applications, do we want our materials to work in the elastic regime, or do we mind working in the regime where plastic deformation occurs? We definitely want to stay in the elastic regime. I think, let's say, if you were crossing the Tacoma Narrows Bridge and you noticed slip bands on the cables that were supporting the bridge, you would start to get a little bit nervous. Therefore, as materials scientists, we're very interested in finding the stress level at which plastic deformation is going to begin. When the material slips, we say that it's yielded. That's one of the learning objectives of this chapter. We want to talk about yield strength, or the 0.002 strain offset, or the 0.2% strain offset. Here is a stress-strain graph. Look first at the point P, where the graph stops being linear. We call that the proportional limit, or the elastic limit. It can be a little bit hard to identify that in an actual graph, and I'm sure we could have debates about exactly what stress that point occurs at. Therefore, we have this definition where we draw a line that's parallel to the linear portion at a strain offset of 0.2%. That is starting at 0.002 on the strain axis. Where that parallel line intersects the stress-strain graph is what we call the yield strength of the behavior, sigma sub y. There are more complicated ways to define the yield strength in cases where the elastic portion is nonlinear, or some materials even have multiple yield points. Here's a more exaggerated version of the stress-strain graph so you can see what's going on. Here the elastic limit is about 35,000 psi. If we were to apply that amount of stress and release it, the sample would go all the way back to its original shape. However, if we apply a stress of about, let's say, 38,000 psi or so, then when we release that, the sample will be left with a 0.002 strain. That is, the sample is permanently deformed. It'll be elongated by about 0.2%, and that's definitely noticeable. That's what's inspiring our definition of the offset yield strength, or the yield strength of the material. I would like to stress, see what I did there, that the yield strength is a lot closer to the elastic limit than what you might think. The previous diagram was rather exaggerated. Here's a more typical one. If you draw a line that's parallel to the linear portion of the engineering stress versus engineering strain diagram, and you begin that line at 0.002, that's 1/10 of 0.02, you can see that the intersection will be very close to the point where the graph stops being linear. They differ by maybe only about 1,000 psi. Again, here's the rationale for the yield strength. When you apply the tensile stress, you're going to get a rather large strain. Most of that, in fact almost all of it, is going to be recovered when you remove the load, except there'll be some remaining plastic strain equal to 0.002. That's permanent, and it's going to stay there even after the load is removed. Here is a diagram comparing the yield strength of various classes of materials. Note that the vertical scale is a log scale. As you might expect, the yield strength of metals is much greater than that of polymers. We don't really have measurements for the yield strength of things like ceramics, semiconductors, and composites, because they generally fracture before they yield. For example, if you were to take your grandma's favorite porcelain doll, don't actually do this, and try to stretch it out so that it were permanently 2% longer than it was before, you wouldn't be able to do that. The material would fracture before it began to yield plastically. As one of the learning objectives of this chapter, let's talk about tensile strength. Another name for tensile strength is ultimate tensile strength, or ultimate stress. It's the maximum possible engineering stress that you can sustain in tension. Basically the peak of the engineering stress versus engineering strain diagram. Here's the tensile strength marked off on our teaching diagram. If you look carefully at the sample when it's being stretched, you'll notice that necking begins to appear at the tensile strength point. That's basically where the area starts to decrease in a localized region of the sample. We have to make sure to say localized because before this point, the stress is still causing the area to decrease, but it's decreasing uniformly over the entire length of the sample. Let's take a look at the stress versus strain curve for steel. Let's look at the red curve for now. Once you see necking begin to appear, what do you think is going to happen to the load-bearing capacity of the sample? Well, not surprisingly, it decreases. You need less force in order to continue deforming the sample. That is, to continue moving toward the right on that red curve. So after the tensile strength point is reached, what happens to the engineering stress? It's going to decrease. So in summary, the maximum load and the maximum engineering stress occur at the tensile strength point. Here's a diagram, again with a log scale, comparing the tensile strength of various classes of materials. Ceramics top the list, followed closely by metals and composites, and those tensile strengths are much greater than those of polymers. Here's the diagram that goes with an example problem in your textbook that you should become familiar with. Notice that the tensile strength is at the top of the curve there at about 450 megapascals. Make sure that you can find the yield strength from this diagram as well. Remember that you're trying to draw a line that is parallel to the linear portion of the stress-strain graph, and you begin that line at 0.02 on the strain axis. The inset shows a little zoomed-in version of that portion of the graph, and you see that the yield strength is about 250 megapascals, or 36,000 psi. This is a good practice problem for when you're given the data in table form rather than in a graph. Please pause the video and unpause it when you're ready to check your answers. Young's modulus is the slope of the stress-strain curve in the linear portion, so 1.0 times 10 to the 7th psi. The elastic limit happens when the stress and the strain are no longer increasing linearly. We can see that that happens at about 35,000 psi. Tensile strength is the maximum stress. We read that right off the table as 40,000 psi. The maximum load that can be sustained is going to be 8,000 pounds, as we again can see that on the left-hand side. And finally, the change in length of the specimen at a tensile stress of 37,500 psi. We look for that value in the stress, and we see the corresponding strain, and from that we can calculate the change in length. We find that it's 0.03 inches. Okay, if you're a comic book nerd, you'll know that this satellite belongs to the Justice League of America, and it's placed into orbit precisely at that distance because its period around the Earth will be 24 hours. That is, it is geostationary. It hovers above a fixed point on the Earth. Once you have a geostationary platform, you can imagine lifting things up into space using a space elevator or skyhook. This would be a lot cheaper than launching things into space after you've invested the money to build the skyhook. Supposedly, this might happen by the year 2050. So the natural question is, what material do you build the cable out of? So looking at the choices in this table, which normal material is best? Do you think you're going to need more information? Well, as you can calculate, you need to know the strength to weight ratio, so you need to know the density of the material. It turns out titanium is the best material to use among these choices. So I'd like you to estimate without calculus the stress in a solid uniform cross-section space elevator cable. Would any of these materials be strong enough? Well, if you go ahead and try this problem for titanium, just imagine a cylinder whose volume V would be 36 million meters multiplied by the cross-sectional area. The weight without calculus would just be mg, or rho times the volume times g. And then the stress would just be the weight divided by the cross-sectional area. The cross-sectional area cancels out of your calculation, and you'll find that the stress is about 1.6 times 10 to the 12 pascals, which is about 3,059 times too heavy. So that's not going to work. You might think about having a hollow middle to the cable. However, the stress is going to be the same at every height as it was before because the cross-sectional area cancels out. Here's the calculation without calculus, assuming that the weight equals mg. No ordinary material comes close enough, but there's an outside chance that carbon nanotubes might work, or maybe genetically modified spider silk. This article says the space elevator might cost over 9.5 billion. That seems to be a vast underestimate to me. Here are some ideas that sound pretty far-fetched about what a space elevator could do. Here's some more speculation about space elevators. They claim that we might be delivering packages to an altitude of 1,000 kilometers as soon as 2025, but we'll see about that. So we did the problem without calculus. Using the expression that the weight equals mg is assuming that the gravitational field is exactly the same over the entire length, or in this case, height of the object. That's really not true for something that stretches into geostationary orbit. Here's a rather lengthy problem that looks into the space elevator with calculus. Please pause the video and resume when you're ready to check your answers. To find the speed, we use F equals ma. The attractive force is just the gravitational force between the Earth and the satellite. The ma is just given by the mass of the satellite multiplied by v squared over r. We can go ahead and solve for v as the square root of g times the mass of the planet divided by r. That's the circled expression. We can relate the speed v to the period by using the period equals 2 pi r over v, so we can go ahead and solve for the radius of the orbit in terms of the period. That's the other circled expression. By putting in the desired period of 24 hours, converted to seconds, 86,400 seconds, we can go ahead and find an r of 4.23 times 10 to the 7th meters. That is about 6.6 Earth radii. Now we want to find the weight of the cable. We have to use calculus here because the gravitational field varies from the bottom of the cable to the top. So imagine a thin slice, a disk if you will, going right through the cable. The mass of that little slice will be rho times the cross-sectional area A0 times the height of that disk, dy. The weight of that one little piece is as shown. It's going to be big G times the mass of that piece multiplied by the mass of the Earth divided by y squared, where y is the distance between that little piece and the center of the Earth. To get the total weight, we need to integrate this from the lower limit of y, which will be the radius of the Earth, out to the upper limit, which is the geosynchronous radius r. And we go ahead and perform that integral, which is fairly elementary, to get our answer. To find the stress in the cable at the top, we take the weight of the cable and divide it by the cross-sectional area A. We find that expression, which is to be measured in SI units. That must be less than the tensile strength. Writing it all out, we see that that is the condition that we need so that the cable will not break underneath its own weight. Not surprisingly, a small density rho will help, as will a small planetary mass, m planet. Those are pretty stringent conditions, but we've made some assumptions. How can we relax some of these assumptions to try to make a better space elevator? Well, how about we try a cable that gets a little bit thicker with altitude? That way at the top, we have a large cross-sectional area to hold the large weight that's underneath it. Plus, gravity gets weaker as we rise, so that thick cable at the top won't penalize you as much as a thick cable at the bottom. But of course, you still need the cable to be able to haul things up, otherwise there's no point to it. So we've still got quite a problem to solve here. You can see that principle, but in reverse, when you look at the design of tall buildings. These buildings are suffering compressive stress, so they're thicker at the bottom than at the top. There's always a relevant XKCD cartoon for everything, it seems. There are some people that believe that this is never going to work, even with carbon nanotubes. This learning objective is to talk about the mechanical property known as ductility, which we can define in several ways. Ductility measures the degree of plastic deformation at failure or rupture. Imagine a piece of saltwater taffy that you stretch between your hands. It will stretch out quite a bit before it breaks or fails. As you can see, that type of deformation is plastic because when you grab it and pull it out like that, if you were to let go, it does not spring back to its original shape. You've permanently deformed it. We measure ductility in two possible ways. The first is percent elongation at failure. We're only interested in the plastic deformation. So after the material breaks, we put the broken pieces back together to measure L final. We're not interested in the amount of elastic deformation that was recovered after we took the load off. The other way to measure